Welcome to Group 27's presentation on our senior design project, the ARM Position Sensor. My name is Brendan Hurley, and I'll be walking you through kind of our product design. And so we were first approached by our stakeholder, Philip Ness. His idea for this was simply to track the position of a human arm through three-dimensional space. And we took this and kind of thought of where it was applicable and started to think of physical therapy, weight training, sports. And so our goal here today is to present the product that we've created and hopefully help these areas as well.
My name is Cody Conrad, and I will be presenting the product overview, starting with the power regulation and source. We got a TPS 63001 as a buck boost regulator. This is outputting 3.3 volts to our microcontroller to accommodate the NPU 9250's power requirements. We are also using a LiPo battery for our source at 850 milliamp hours. And there is also a charging IC on this power block that allows us to charge on board. Moving to the microcontroller, we have an ATmega 328P. It's the easiest one to prototype since the Arduino Unos use the same chip, and also there's a lot of information readily available for them. We did have a couple problems with that chip being 8-bit and lower memory size than most, and we will talk about that more later on. The code required was fairly intensive, and there's a lot of code to support all these devices along with some algorithms to give us some more data on the data we're capturing. Over here we have the SRAM, and this was more of a safety net for the most part, for the reason that we may have a speed constraint and we didn't end up really meeting it. We ended up being able to capture live data, but we were definitely considering the possibility that our microcontroller may not be able to handle as much data as the sensors are putting out. But this allowed us to temporarily store data and send it out over Bluetooth if needed. We have the Bluetooth transmitter that captures everything and sends it out to a phone or computer for analysis and capture. And finally, the main product that's on our board is probably the NPU 9250, and this is the device that actually captures our accelerometer, gyro, and magnetometer data to actually get live feeds from people's motion and gather the data that we required.
All right, we're going to be demoing the system here. My name is Chad Jabot. Cody's going to be our guinea pig here. He's got the device on his right shoulder there. For the prototype purpose, we have the device held on by a Velcro strap. If this were to be further researched, it would be developed into a full sleeve that would incorporate the sensor, the main board sensor you're seeing there, along with two additional sensors down the arm that would be located at the elbow and at the wrist. So as you can see in the data as he's moving, we have acceleration, angular velocity, and relative position, which is data from the magnetometer. All three of those are coming through in 3 axes with the various colors. One of the problems that we had mentioned earlier was the ability to send data in real time, which in our initial prototypes, we weren't able to achieve the speed necessary to do that, so we introduced the SRAM to record data and then send it out in a chunk. Once we had the PCB built, we were able to get the data rates to be higher and be able to actually send real-time data like you're seeing now. As I mentioned, the data we're seeing now is from a single sensor located on his upper arm. We do have the ability to do the other 2 sensors, which would give even more detailed motion of the entire arm rather than just the generalized movement of the upper arm as it is now. The range of this device is about 50 feet. or even a little bit further. So for applications of sports and weight training and stuff, the phone or computer does not need to be directly with the user. It can be a little ways away and still be able to record data. We're going to talk a little bit about some of the issues we had, and this really represented a good portion of our time on this project. We spent fighting some of these communication issues. One of the biggest ones that we ran into, which we didn't actually solve until very close to the end of the project, was the SPI mode. With the SPI data transfer protocol, there's a clock polarity, whether or not a 1 is represented as a high versus a low on the SPI clock. And then there's also the difference between whether or not the device latches the data bit on the rise of the clock versus the fall of the clock, and then reads on the opposite one. And the reason why this problem wasn't caught sooner was that the registers that we were writing to on the sensor, we believed they were being written to, and therefore communication was verified. However, that turned out not to be the case, since the registers that we were writing to, the values of those were the default values. There was also an issue with the auxiliary I2C bus with the MPU sensors. The way this works is that the microcontroller talks to the main sensor via SPI. This sensor is where the accelerometer and gyro data is coming from. It then talks to a separate sensor via I2C to retrieve the magnetometer data. Obviously there's a difference in clock speeds here, so the SPI data actually, or the SPI protocol, has to be throttled back a little bit to allow time for this communication to happen. There wasn't any real good documentation on what that delay should be, or even that there should be one, so that took us some time to troubleshoot to get reliable data coming back from the magnetometer. These sensors also have the ability to communicate solely in I2C mode, which we also attempted since we were having troubles with SPI. But we ran into quite a bit of problems with one of the devices holding onto the data line and not dropping it, which locked up the I2C system. It was hard to troubleshoot that because, again, now with the magnetometer being on I2C and the main sensor being on I2C, and not being able to access this information with a scope, it was hard to diagnose what that problem was.
Alright, so now I'm going to discuss the system changes that we would make to our project to kind of alleviate some of the problems that we are experiencing and also make it an overall better product in the future. So starting off, as mentioned before, our 18 mega 328p doesn't have quite the memory capacity that is required to unlock some of the potential that we have in our sensors. The sensors actually do have a built-in, they name it DMP processor inside of them that's capable of converting all the raw values into quaternions and headings and pitch and roll inside the chip, so it offloads a lot of the processing from the processor itself. So stepping up to something like the ARM M0 Plus, or maybe even an M3, we would have the memory capacity to unlock that and also unlock a lot of features to actually make us capable of capturing more data and more sensors if needed. So going to sensor implementation, currently our 9250s are a system in package. As Chad mentioned earlier, they have the magnetometer hooked up into an auxiliary I2C bus that can't be accessed outside of it. Did cause some problems, and a lot of the problems could have been alleviated, and also would allow us to use a higher quality magnetometer as well. So switching and making them independent chips, for instance, we could still go with InventSense for the accelerometer or the gyro, and use their MPU 6500 series, which is just the accelerometer and gyro, and then go with another company to get the actual magnetometer chip and put all of those on nodes for PCBs and put them all over the ARM, and we'd be able to control our data and our info a lot cleaner and more streamlined. So battery capacity was also not super critical, but we could cut down on weight and size a little bit by switching it from an 850 to a 250 milliamp hour battery. The 850 milliamp hour battery right now is capable of lasting far past 10 hours currently in all of our testing. So we definitely have a lot of room to actually use a smaller battery and still meet our requirements for this project. Finally, the actual PCB could be scaled down, and one of the main things is to integrate the Bluetooth module onto the PCB itself. In the demos you can see the Bluetooth module actually sticks up out of the PCB, and obviously that's just something that can get snagged or caught. The next one is mounting, which goes into scaling the PCB, make it smaller, more compact. It's currently hooked up and set up in a way that allows us to prototype very easily, and by cutting out all the extra pins and peripherals that we don't need, we can make it much smaller and allow everything to be mounted on a sleeve, compression sleeve, for a really streamlined and comfortable fit.
Alright, this is Brendan Hurley coming back at you. I'm going to be walking through the GUI and the user interface aspects of our project. So here we have the Bluetooth code. We're running it through a parser to get the raw data from the accelerometer, gyroscope, and compass. From here we'll be running a couple basic algorithms just to organize and store into the GUI, and I'll show you that in the demo in just a moment. So let's get started. Alright, so this is our GUI from the initial boot. There's 3 graphs on the right side, along with a 3-dimensional model of basically 3 sensors in 3D space, and eventually they will move according to the accelerometer, gyro, and compass data. Down here we can represent the actual values as we slide through the data points. Also allowing to specify a wrist, elbow, or shoulder sensor. And up here in our options menu we have the choice of doing Bluetooth. Later on, after we've actually captured some data, we can click on the replay, and there will be a file here after collecting some data. So let's start by collecting some data here. Alright, so as you can see, we found the target Bluetooth device, which is the HC-05, and then we will be going back. So there's nothing currently on the 3D model that's happening. However, you can tell that our graphs have started to show data. So right now the sensor is sitting still, and so all the lines are pretty flat, especially the accelerometer, which just has the gravitational force right here, and then the other axes have no acceleration in them. And then same thing for gyro and magnetometer as well. This is going to be a demo for showing the sensor moving. So previously we showed just a standard stationary position, and now I'm going to move the sensor around just to show that the data is different. And there we are. You can see all 3 of the plots are different. Future improvements for this is obviously getting the 3-dimensional model to work. and then also updating these live as the slider is going. You can also see that now there's a BT file 0. This is the data that was collected from the run that we just did, and so the user would be able to click on this and then use the slider to go through the data and basically see how they're set or how their repetitions for physical therapy were accomplished, quality, as well as tips for improvement.
This concludes our senior design presentation, and although we did not accomplish many of the goals that we sought out to achieve, due to the I2C bus not working on the auxiliary for the magnetometer, the sporadic prototyping issues that we experienced throughout the system, we do believe we have a framework for a very solid product in the future. Thank you.